Hello, so today we are going to take a look at this problem, which is part of today's contest, context 304. So the problem is maximum number of groups entering a competition. And what the problem says basically is that we get a group of, or an array of grades representing the grades of a set of students. And what we want is to enter all these students into a competition in an ordered non-empty groups, such that the ordering meets these conditions. So yeah, you don't need to worry about that statement, just let's focus on these two conditions here. So the sum of the grades of the ith group of the students in the ith group is less than the sum of the grades of students in the i+1th group. So you have a set of groups. The sum of the values of the grades of the group at I position is smaller than the one for the group at position i+1. So that's the first condition. The second condition is that the total number of students of the ith group is less than the one for the i+1th group. So basically, the size of the group at position I is smaller than the size of the group at position i+1. And the goal of the problem is to return the maximum number of groups that can be formed. So let's first see this on an example. So we have this array. What we can do, so we can create a first group of just one element, and here they choose 12. Then we can create a second group of two elements, so the length is bigger. The length of i+1 group is bigger, which is what we want. The length of the ith one is smaller than the i+1, so that's valid here. And the sum is also smaller because this is 13 and this is 12, and the count here is 1, the count after that is 2. So that's the second group. The third group has 3 elements, so the size is bigger. So this one size is smaller than the next one, and the sum is also bigger, right? 13 is smaller than 18, and so we have the two conditions valid for all of these 3 groups. And now once we do this, we have all the 6 elements in the grades array, so we have all the students, and so we can return 3. For the second example though, we can't create 2 groups, because if we create 2 groups, then each of them will have 8, and so the sum will be equal and the length would be equal, and we can't do that because that's these conditions won't be valid. We can't have a group of size 0, right? It's non-empty groups here, and so the only thing we can do is put one group of 8, 8, and so we return 1. So that's the problem. Now, one thing I would say that they maybe did intentionally is that the explanation here misleads the solution, right? Because they pick as the first element 12. But actually, if you think about it, it's better to kind of just take the smallest, because then you have a higher chance of the second group having a larger sum. Right? So picking the smallest element, that's better. The other thing is, if you just start from size 1 and keep increasing by 1, that's the best you can do, right? Because we can't have an empty group. And so to maximize the number of group, let's just increase by only 1, just enough to validate this condition. Because if we increase by more than 1, let's say 2, then we have less chance to have the maximum number of groups, if that makes sense. So with those two considerations, let's take a look at how we can solve the problem. Okay, so let's see how we can solve it. So actually, what I said earlier is what we can do here, which is, let's just apply the fact that taking the smaller value first is better. But the more important one is that we can't have an empty group, right? So we'd have to start with a group of size 1, okay? And then what we can do is since we the group of the size of group I has to be smaller or equal than the size. So this is, by the way, this, I'm just denoting size here, has to be smaller or equal, smaller actually, not equal, has to be smaller than the size of group I plus 1. So the easiest way to do that, but at the same time maximize the number of groups, okay, so what this would mean is that while we will assign, or we will have group of size 1, we'll have just one student, right? And then a group of size 2 would have 2 students, group of size 3, so each time we just increase by 1 to do the minimum to have this condition be valid, right? And then each time we can just pick the smallest value, the next smallest values, right? That way we ensure that the sum is also smaller, right? So 3 students, and then at the kth group we need to have k students, right? And so what we want here is to have this sum, because we only have the array of grades, right, which is, let's say, of size n. We want this sum here to be smaller or equal to n, right? So we can have, maybe we can't fit everything into k groups, right? Maybe we'd have 1 or 2 that can be in any group, right? Because we can't form a last group with these, so those may be remaining, but we will need to get as close to n as we can, right? Okay, so we need the sum of these to be smaller or equal to n, right? Because n is the size of the array. So what this would mean is that we want 1 plus 2 plus 3 up to the last group we can construct needs to be smaller or equal to n, right? Okay, so how can we translate this into a solution, right? So we know that our upper bound is this n here. So what we can do is just, for our function, just while we haven't reached the n, so we still have elements in grades, we want to keep constructing group. And so while n is bigger or equal to k, so we'll initialize k to be 0, and here I'll say k plus 1. So why k plus 1? Because each time we will construct a group of length k plus 1, right? Because we start from 0, we want the first group to be 1, right? And so we'll increment k, and what we'll do is subtract this k from n, because let's say we construct the first group with just 1 student, right? So what do we have remaining? Well, we have remaining n minus 1 students to assign, right? If we once we construct this, we have n minus 1 minus 2, right? And so each time what we want to do is subtract k, and then we go again and try to construct a group. So what this would mean is that first we'll construct a group of size 1, and so let's say our n was equal to 5. Then we have n now equal to 4. That's the max we can construct. And now we want a group of size 2 because we increment k. And now n is equal to 4 minus 2, 2, right? So now that's all we can construct. We can't construct a third group. Really? So 4, yeah, we can't construct a third group because k equal to 3. That would be, we need n to be bigger or equal to 3. And that's not the case too. So we can't construct a third group because the third group has to have size at least 3 for the conditions to be valid. And so this while loop here will reject that. And then at the end we can just return k, right? And you can see this here is O of n because we do at most n iterations for n to get down to 0, right? Yeah, and so that's pretty much it. So we use this basically greedy solution because to maximize the number of group, we need to grow the group by just 1. That's the minimum we can do, right? And we don't need to actually construct the group. we can just suppose that each time we pick the smallest value, that will get us the condition for the sum of each group smaller than the next one, right? And then we can do using this formula here of the sum of all the group needs to be within the number of grades we have, right? And with that we can just do our while loop. Yeah, so that's pretty much it for this solution. Let's code it and make sure it passes test cases. Okay, so let's write down the solution we just mentioned. So what we need is to initialize n and k. So n is the length of grades array, k is equal to 0, and we need to maintain while k is bigger or equal to n, while n is bigger or equal to k plus 1. We are constructing a group of size k plus 1, and so we subtract it from n, so that we don't take it into account for the next group, and then at the end we return k. So pretty simple. We don't need to even look at the elements in grades. We just assume that each time we are picking the smallest. So if we run this, and submit. Okay, so that passes test cases. Now, as I said, this is open. Now another idea to think about is that is to use actually binary search. So let's look at the concept there and make sure we understand. Okay, so what's the idea behind the binary search solution? So if we take what we said here, right? Since we explained that, we don't need to go over it again, but we know that we need this to be smaller than or equal to n, but we want at the same time to maximize this, right? We want to maximize, to get as close to n as we can, because we want to maximize the number of groups, right? And so this is exactly where binary search can be useful. Is you want to maximize a value while maintaining a condition, or you want to minimize a value while maintaining a condition as well. So what would happen here with binary search is we need to just find the pattern where we have a monotonic function. What this would mean is that we need to find a function that is false first until it becomes true. So we need to find a function that is first false and then it becomes true, but once it becomes true, it keeps being true. So false, and then once it becomes true, it keeps being true, or it's true and then once it becomes false, it keeps becoming false. So this is what we mean by monotonic. And so how can we find something like this? So in our case here, right, what we can do is find x such that it's smaller or equal to n. So we know that 1 plus 2, let's say n equal to 5, right? This is smaller than 5. 1 plus 2 plus 3, that's equal to 6, right? So it's bigger. And then if you add more, let's say 3 plus 4, it's still bigger than, so this is bigger than 5, it's still bigger than 5, right? So as you add more element, it's still bigger than n, right? So basically once it becomes true, it will only increase, and so we will keep being bigger than n. So we have actually this pattern here. So if we use the function, so if we use as our function basically 1 plus 2 plus x bigger than n, then we have this pattern, right? If we want to use smaller or equal to n, then we would have this pattern here, right? But I'll choose to go with the first one. So bigger than n. And so if we choose this pattern here and we have false, 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 true, so what are we looking for? We are looking for the last value where after it we would be bigger than n. So that means we will maximize this value, right? Because if we increase more than that, we will get over n, and that can happen because we have only grades only that number of grades equal to n, right? And so what this would mean here is if we do this function, the result for k we are looking for is actually here, the last f, last false value. Okay, but with our binary search on this pattern, what we will get is actually the first true. We'll get the first true. But then it's easy, we can just do the first true minus 1, and that way we'll get this one, right? So that's the idea we will go for. And so our function would be, just to reiterate, our function here would be f of x is equal to 1 plus 2 plus x bigger than n, right? And this is actually just any sum of 1 plus 2 plus until n is actually mathematically just equal to n multiplied by n plus 1 divided by 2, right? And so we could just have this bigger or equal to n, bigger or equal, sorry, to, yeah, this would be, yeah, let me actually just say it again. So what this would mean is that our f of x here would be just x multiplied by x plus 1 divided by 2 is bigger than n. So this is our binary search function. And now we can just write our binary search in whatever format you are used to, and then find this point here. And once we find it, we just return it. Okay, and this point is the k here we are looking for, which is the x for this function, which would be this k we are looking for. And the one thing you will notice is that the size of the last group, that's actually the number of groups we have, right? So if you have, so that's why this k, we only need to find this k here. So the size of the last group is the number of groups we have, because let's say you have 1 plus 2 plus 3. You have 3 groups, right? So this k is the what we are looking for, plus 3 plus 4. We have 4 groups, that's this here, and you get the idea. Yeah, so let's write this and make sure it passes test cases. Okay, so let's write down our binary search here. So first we'll just have the length of the grades and we need, for binary search, we need low and high. So for it to be false, I'll start with -1 and with high being n, because that means bigger than n is going to be false there, and same thing for -1 as well. And now we'll just write my usual binary search, which is high minus low. So basically, just before they meet, that's what I want to get. And mid is going to be low plus high plus 1 divided by 2. And now what we want is if, so remember what we are looking for is x plus 1 divided by 2 is bigger than n. And so x, we just replace it by n. By x, we just replace it by mid, sorry. So divided by 2, we want this to be, I'll just add parentheses to make this clear, to be bigger than n. Now, let's see, where would our mid be here? Where would we do, what would we change, right? So this is the pattern we said. So let's say this is true. That means we are at this position here, or something here, because it's true. So what, because we have true here. So what this would mean, so this is where our mid is, and our high is somewhere here. So I'll just add more true here, and our low is somewhere here. Maybe it's at a true position, maybe it's at a false position. So what do we want to do at this case? So potentially this true could be the last true, we don't know. So maybe our mid was here, we can't tell, right? So what this would mean is that we need to push our high just to be here, right? Just to be here, so that if our mid was here, we'll still take the last true into consideration, but our low won't change. So what this would mean is that our high is going to be equal to mid. Now else, what is the else case? Else is f is actually here, and low is somewhere here, somewhere in the false direction, and high is somewhere after. It can be on a false, we don't know, right? And so in this case, what should happen? Well, we are looking for the first true, right? And so what this would mean is that, well, we should advance our low to be after mid, because then we'll have a chance to find the true value, right? So what this would mean is that we will need our low to be equal to mid plus 1. There is no use in assigning it to mid because we know mid is false, right? And at the end we have our value low. We said that if we will want to try low minus 1 because we are at the last true, right? And so what we wouldn't want to do here is check if this condition is valid for low, then if the condition of remember what we want, the condition, that final condition that we want is that everything k is smaller than or equal to n. If this is valid for low, then we can just return low. Otherwise, that means we are not at the last false, we are at the first true. And so we subtract minus 1 and return that, okay? So what this would mean is that here, this sum here is just low multiplied by, is just this formula here, multiplied by low plus 1 divided by 2. So we just do that, plus 1 divided by 2. And then, so if this is smaller or equal to n, that means we are done. We found our solution, so we just return it. Otherwise, this is not the last false, this is the first true, and so we return low minus 1 to get the first false, to get the last false here, right? And that's pretty much it. So let's run this. So this is just binary search. Feel free to write it in whatever is easier for you. Yeah, so we need here. And let's submit. Okay, so that passes test cases. And so this one here, it's binary search, right? On n. And so it's over again. So it's even faster than the previous solution. Yeah, so that's pretty much it, I think, for this problem. Hope this was easy to understand. Please like and subscribe, and see you on the next one. Bye.